So let's take a look at these checkpoint questions here. The first one, when a substance moves up its electrochemical gradient, does it require energy or does it release energy?
It requires energy since it's moving up.
Excellent, perfect. Yes, it requires energy because it's moving against its gradient or up that electrochemical gradient. Perfect. And then the opposite would be true, right? If it's moving down that gradient, it liberates energy instead of requiring. Number 2 here, suppose that a transport protein couples inward flow of sodium with outward flow of calcium. Is co-transport or counter-transport occurring?
It would be counter-transport because they're moving in different directions and they're not moving together in the same direction.
Excellent, yes. So again, because of the opposite movement of these two ions, it's going to be counter-transport and not co-transport, okay? And then number 3 here, suppose that glucose moves into a cell by means of sodium-linked co-transport and that glucose concentrations are 2.5 millimoles inside the cell and 1 millimole outside the cell. The lead here, is sodium being transported actively or is it being transported passively?
It would be actively because it needs energy in order to get into the cell because that's where the higher concentration of it is, which is against its natural gradient.
Okay, so which one would be moving? Remember, we're asking about sodium here. So think about what sodium movement would be. Right, so I think you're probably thinking.
So is this saying that sodium is moving out of the cell then?
So sodium will be moving into the cell because it's co-transport. So let's draw a cell here. We've got a cell, right? We've got sodium moving in. We've got this coupled to the movement of glucose also moving in. And then they've gone ahead and given us the glucose concentrations, right? Which is really important to figuring out how glucose is moving first. And then we can figure out how sodium is moving. So if glucose is at a higher concentration inside the cell and a lower concentration outside the cell, is glucose moving actively or passively here? I think I'm hearing some.
That would be active, wouldn't it?
Excellent. So this would be active. So glucose's movement, the movement of glucose would be active. And so what would that make the movement of sodium?
Passive, possibly?
Passive, perfect, passive. Passive is correct. All right. So essentially the energy that's required for glucose to move against its gradient is being liberated as sodium moves passively along its gradient, okay? And so the only way that we could have deduced this is by first figuring out how glucose is moving based upon its concentration gradient. So because glucose is moving actively, it's going to need energy from somewhere, as this is co-transport, right? This coupled movement here. And so it's going to get that movement. Sodium must be moving passively in order to liberate that energy, okay? If, for example, they gave us opposite concentrations here, let's say this was decreased concentration and a higher concentration of glucose, right? We would now have a gradient that favors glucose moving passively. It's going to kind of cross this out, passively instead. And so this being coupled would allow us to deduce that sodium would be moving actively. Okay, I hope that makes sense. So really understanding the concentrations of glucose, how glucose is moving first, and then because this is a coupled movement, co-transport, we know that sodium has to be moving passively. All right. Okay. All right, so we're gonna go ahead and switch over. We're gonna move to that third packet here, which is membranes part 3. And this again is getting into osmosis, or the movement of water, okay? And so we'll start with this first objective to basically explain how a difference in solute concentration, excuse me, across a membrane can cause the movement of water and explain the distinction between osmolarity and tonicity of a solution, okay? So really how water moves across membranes. So water moves via diffusion, and this diffusion is described as a process called osmosis, okay? So osmosis is the diffusion of water through a membrane. It's always passive, so again, it's always down the concentration gradient of water. It's unaffected by the membrane potential, so there's no electrical force that moves water. Water is uncharged, and so it doesn't obey any of the electrical driving forces that we described earlier. And it is purely driven by the concentration gradient or the chemical gradient, okay? And so if you look at these two scenarios here, we've got a solute concentration of 0.3 moles, meaning that 300 milliosmoles are dissolved in this solution. So that gives us a water concentration inside the cell of 55.2 molar, okay? Outside the cell, we have 0 solute concentration and then 55.5 water concentration. And so what we see is that this creates a gradient for water. So water is at a higher concentration outside the cell because it's pure water. It's at a lower concentration inside the cell because it's got more solute dissolved inside the cell. And so that is that water gradient, that's the concentration gradient that facilitates water movement from the outside of the cell where we have pure water to the inside of the cell where there's less water, okay? Likewise, in our scenario B, we can see a similar movement of water according to a gradient. So inside the cell, we have a solute concentration of 300 milliosmoles dissolved in that solution, a water concentration of 55.2. And then outside the cell, in this scenario, we have a lot of particles dissolved as well. So we have a higher solute concentration, so 1,000 milliosmoles of particles or solutes dissolved outside. And that gives us a water concentration of 54.5 mole, okay? So essentially, we're going to see a gradient of water in the opposite direction. Higher water concentration inside our cell, lower water concentration in the surrounding environment outside the cell. And so water is now going to move from the inside of the cell to the outside of the cell. Okay, so all of this, just to say, water always obeys its concentration gradient. It always moves according to its high to low concentration or passively. Okay, let's speak about what osmolarity is. And osmolarity is basically the total solute concentration of a solution. It's a reflection of how many solutes or particles are dissolved in that water or displaced in that water. And so this is where we get to the distinction between the mole versus the osmole. So the mole is the total amount of that particle, right, of that molecule, right? So we can have 0.1 mole of glucose, and we can disperse or dispense that 0.1 mole of glucose in 1 liter of water, and that gives us an osmolarity of 0.1, okay? If we take another type of molecule, for example, sodium chloride, we can have 0.1 mole of sodium chloride, but when that is displaced or dissolved in a liter of water, the osmolarity is different, right? The osmolarity here is 0.2 osmoles because each of those solutes will then further dissociate into their relative parts. And so we're going to see the dissociation or the dispersion of that sodium chloride into sodium and chloride, which each have their own osmolarity, each contribute to the osmolarity of that overall solution, okay? So really just to say or to highlight here that the osmolarity differs from the mole because it's the total solute concentration dissolved or displaced in water. Usually we measure osmolarity in terms of milliosmoles. So 1,000th of an osmole, and that's just because that's the relative osmolarity within our physiology, okay? Really small particles dissolved in our physiology, in our fluids. And so looking at our osmolarity, the osmolarity of our plasma, this is a measure of our intracellular fluid compartment versus our extracellular fluid compartment, and it's usually about 300 milliosmoles. And what that means is that there are about 300 solute particles dissolved in our plasma, essentially, okay? And now as we speak about osmolarity, we can talk about different types of solutions. We can speak about an isoosmotic solution. This is a solution that is the same osmolarity relative to another solution. Okay, so if we're thinking about a cell that's dispersed in water, if there's pure water inside the cell, pure water outside the cell, or even if there were solutes dissolved, if there were the same amount of solutes dissolved in the solution inside the cell as there are dissolved in the solution outside the cell, we would then see an isoosmotic state, right, or an isoosmotic solution. In other words, we may see, water, again, that one-way flux that we described when we talked about particles moving. We may see that one-way flux of water, but there's no net accumulation of water to either side. We can then speak about a hyperosmotic solution. So if we were to disperse an animal cell in a hyperosmotic solution, then that means that the solution is going to have more solute particles dissolved as compared to the solution inside the cell, to the inside of the cell. And so that would facilitate the movement of water from the inside of the cell where there's more water or a higher water concentration to the outside of the cell where there's less water or a lower water concentration, again, according to that gradient. And we can see how this would be detrimental to our cells, right? This would create a crenated or a shriveled up or crumpled up cell because most of that water will be moving from the inside of the cell to the outside of the cell. And this is why it's so important for our osmolarity, for our cells to be dispersed in that isoosmotic solution. So the intracellular fluid compartment has an osmolarity of 300, but then our extracellular fluid compartment has an osmolarity of 300 so that there's no net accumulation on either side. Another extreme scenario is a hypoosmotic solution. So again, if you put one of our cells, our eukaryotic cells, into pure water, this would cause the cell to rupture or to lyse. This has a gradient that facilitates water moving from that high concentration outside of the cell. Remember, hypoosmotic solution has less solutes dissolved in it. And so in other words, it has more water or higher water concentration. So water would move from the high water concentration outside to the lower water concentration inside. And so this would eventually cause the cell to go larger and larger, eventually lyse or rupture because of that excess water movement. And so we can see how these two scenarios on either side here can be detrimental to our cells. This would cause our cells to be misshapen or distorted on one end if they were dispersed in hyperosmotic solutions, but then they would completely rupture or lyse if they were dispersed in hypoosmotic solutions. Okay, and so the way that we maintain homeostasis relative to our plasma osmolarity is to keep our cells at an osmolarity of 300 as well as our extracellular fluid. All right, now let's speak about the osmotic pressure that is exerted as a reflection of varying solute concentration. So if I have more solute dissolved in one side of the membrane, so let's look at this scenario here. So on side one, I have less solutes dissolved. In side two, I have more solutes dissolved. So I have a water gradient, right? But then I also have a solute gradient, okay? So the solute gradient is from low to high. The water gradient is going to be the opposite. So the side that has more solute has less water, and the side that has less solute has more water. So the water gradient is going to be going from side one to side two. Now we can also think about the pressure that would be exerted as a result of this flow of water. This is called the osmotic pressure. And so that really is the pull of water from side one towards side two. So we can think about the osmotic pressure as the pressure or the force, the ability to pull water to the side that water is moving toward because of its gradient, okay? And so if we were to look at the osmotic pressures here, we would see that the side two has an osmotic pressure of 12.3 atmospheres. Side one has an osmotic pressure of 7.4 atmospheres. And so based upon that, we can see that side 2 has the stronger osmotic pull or the stronger osmotic force. In other words, water really wants to get to side 2 because of that stronger osmotic pressure. Okay. We can also think about this as the amount of pressure or force that would be required to stop or prevent the water to move, right? In terms of really thinking about this as a force, we can think about it in sort of a negative way, right? How much force would be applied in order to prevent this water movement? And so that is another way of understanding or of expressing the osmotic pressure as well. Because the movement of this water exerts a force, we can think about that force in a negative way. How much force would be required to stop that movement? All right. And then at the bottom here, we can see that there's also an osmotic pressure gradient. And so because we have a higher osmotic pressure on side 2, in other words, a higher pull, and a lower osmotic pressure on side 1 or a smaller pull, we then have an osmotic pressure gradient, which facilitates the movement of water from the low side to the high side, okay? So water would move from the side of low osmotic pressure to the side of higher osmotic pressure. In other words, the water moves according to the water gradient, but it's actually moving against the osmotic pressure gradient. All right, I hope that made sense. Different ways to kind of express this idea of osmotic pressure. Let's now speak about tonicity. And so tonicity is the water gradient that moves across a membrane, but this is really a reflection of only the impermeant solutes. So only the solutes that cannot themselves cross the membrane, okay? And so it's going to be different from the osmolarity because we're not looking at all the solutes, right? There can be more than one solute dissolved on either side of our membrane, but tonicity only takes into account the solutes or the particles that cannot move across the membrane. All right. And when we speak about tonicity, we can, think about a similar reflection to what we saw with osmolarity. We can have an isotonic solution. We can have a hypotonic solution. And then we can also have a hypertonic solution as well. Okay. Now let's kind of clarify this here, the difference between osmolarity and tonicity. So when a solution is the same in terms of its osmolarity, inside and outside of the cell, we say that that's an isoosmotic state or an isoosmotic solution. But a solution can be isoosmotic, but also hypotonic, right? Not isotonic, but hypotonic, okay? And let's explain why. So on the left here in scenario A, we've got a cell that's dispersed in a solution. We've got we've got equal concentrations rather of solutes dissolved in either of those solutions. So the same amount of solutes dissolved inside the cell as we see on the outside of the cell. And so we can think about this as being an isoosmotic solution, right? The osmolarity inside the cell, in other words, the amount of dissolved particles is the same inside the cell and outside the cell. But if we think about the same exact scenario, but we're now thinking about the tonicity here and not the osmolarity, we're going to completely ignore the solutes in yellow. The solutes in yellow can actually permeate the membrane. They can go across that cell membrane. And so when we think about tonicity, we completely ignore any solute particles that can move across the membrane. And so thinking about this initially isoosmotic solution, it is a hypotonic solution because there's less of that non-permeant solute in the outside of the cell and more of that non-permeant solute on the inside of the cell, okay? All right, I hope that makes sense. So that creates a gradient for water to move from the outside of the cell to the inside of the cell because the solutes in yellow can move themselves. They can become at equilibrium. And so we're really only taking into account the osmolarity of the solutes in purple because they themselves cannot cross the membrane. All right, hope that makes sense. So we can have a solution that is isoosmotic, but is hypotonic instead of isotonic. All right. And so here's just a table that kind of further highlights the distinction between osmolarity and tonicity. So again, osmolarity, we can have isoosmotic, hypoosmotic, hyperosmotic. And then tonicity, we can also have those same states, isotonic, hypotonic, hypertonic. But again, here we're only thinking about solutes that cannot move across the membrane. When we think about osmolarity, we're thinking about all of the total solute particles that are dissolved in either solution. Okay. So at the end here, this is just a scenario or an illustration to highlight that movement of water once again. So in A, we have a high water concentration outside and a low water concentration inside. So can anyone describe the state of this solution on the outside here? Is it hypertonic or hypotonic? Or hyperosmotic or hypoosmotic?
Hypoosmotic?
It is hypoosmotic, excellent. And again, hypoosmotic means that there are less solutes or more water, right? So with respect to the inside of this cell, this solution is hypoosmotic. And again, this is all of the solutes dissolved. We're thinking about when we think about osmolarity. And so we have more water outside the cell, less solutes outside the cell. And we can just look at the osmolarity of these two solutions to further clarify that, right? We've got less solutes dissolved. We have an osmolarity of 150, more solids dissolved, we have an osmolarity of 300. And so this facilitates a water movement inside the cell or outside of the cell. Where is water going to move in this scenario?
Because it's hypoosmotic, it's going to go inside the cell.
Excellent, yes, perfectly correct. So because of the hypoosmotic state, water has a gradient from high concentration outside, low concentration inside. It's going to naturally move into the cell and equalize those concentrations, right? The osmolarity of both of those solutions. Likewise, at the bottom here, we see an alternate scenario. So we have more solutes dissolve on the outside of the cell, less solutes dissolve on the inside of the cell. And again, that is reflected in the osmolarity of these two solutions. So it's a 600 osmolarity outside, and then the osmolarity of the solution inside is 300. And so the water would move in the opposite direction, right? It's going to move from the inside of the cell where we have more water, less solutes, to the outside of the cell where we have less water, more solutes. And that would cause the cell to shrivel up as water moves from the inside to the outside. Okay, this first scenario would actually cause our cell to swell and eventually rupture or lyse. Okay,